Hello and welcome back to the Operations Research 1 course. First of all, Happy New Year to us all. May we have all the better things in the coming year. This week we are still going to talk about duality, and we'll start by looking at how we may use the duality concept to perform sensitivity analysis. So let's start. If you recall the dual theorem, it says that the dual solution is CBVB inverse. So now, if we have a set of basic variable in primal and that solution is optimal, it must be that the corresponding dual solution, CBVB inverse, is dual feasible. With that in mind, we are going to perform these three changes, change 1, 4, 5, out of the 6 changes that we've talked about in week 10. And then the basic idea here is that after we make the change, we need to check whether the CBVB inverse remain dual feasible or not. If yes, it means that the current basic variable remains feasible even after the change. If not, it means that the current basic variable becomes not optimal anymore after the change. So the key here is checking if CBVB inverse is still dual feasible or not. Now we are going to use the example of Dakota problem. So here's the primal problem, and we are given the optimal basic variable for the primal. And here is the dual problem for the Dakota problem, and then we have also given the optimal solution for the dual problem. Now we're going to look at the first change in which we change the objective function coefficient of a non-basic variable. So here x2 in the optimal solution is a non-basic variable. You see that the basic variables are s1, x3, and x1. So x2 is a non-basic variable. And then we are going to change the coefficient from 30 to something. So in general, the question is what value of C2? C2 is the cost coefficient of x2. So what value of C2 makes the current basic variable remain optimal? So in other words, what is the price of table such that this set of basic variables is still optimal? So again, the idea in duality is that we are going to check, does the change make the CBVB inverse remain dual feasible or not? So in other words, what values of C2 that keep the CBVB inverse dual feasible, and what value of C2 will make CBVB inverse not dual feasible anymore? So this is what we're going to do. As I've said before, we check the value of C2 that keep the CBVB inverse remains dual feasible. And then remember that CBVB inverse is actually the dual solution. So y1, y2, y3, they are CBVB inverse. Okay, so we are going to use this to do the checking. Okay, so let's start by looking at this. We are going to change this coefficient from 30 to become C2. Now identify that change in the dual problem. In the dual problem, it means that we are going to change that number, the right-hand side from 30 to become C2. Everything else does not change. It means that when we want to check this feasibility of the dual solution, or the CBVB inverse, the only constraint that we need to check is the table constraint, because the other constraint does not change. So obviously this optimal solution is still feasible. Okay, so we rewrite the table constraint to becomes like this: 6y1, 2y2, 1.5y3 greater than or equal to C2. Now plug in the values of y2 and y3. So y2 equals 10, y3 equals 10, and then we get that As long as C2 is less than or equals to 35, the current optimal dual solution remains feasible. From the previous slide, the result says that as long as the price of the table is less than or equal to 35, the current basic variable remains optimal. Remember that in that optimal solution, x2 is a non-basic variable. It means that in the current situation with the selling price of the table equals $30, we do not produce table. That implies if the price of a table is greater than 35, then table becomes profitable to produce. Or in other words, because the current basis is no longer optimal, if the price of the table exceeds 35, then we would like to produce table. Why or how is that the case? We may look at this thing from the viewpoint of shadow price. So now we see that a table requires 3 resources. We have obtained the shadow price of each resource, and then we also know that the amount of resource used to make a table is 6 board feet of lumber, 2 hours of finishing, 1.5 hours of carpentry. So we may calculate the total value of the resource by multiplying the shadow price of the resource times how much each resource is used to produce a table. And then we take the sum, and then we see that to produce a table, we need the resources that equals to $35. Now this explains why if the price of the table is less than or equal to 35, we do not produce table. When the price is higher than 35, then table becomes profitable to be produced. Okay, so now you may see that we may use the shadow price to calculate whether the selling price of our product is good enough for us to produce that product or not. Now let's look at another change in which we changed the entire column of a non-basic variable. Here we change the entire column for x2 or table. So not only the price, we are going to change the entire column. For example, we have kind of, let's say, a new type of table with a selling price of $43, and it requires 5 board feet of lumber, 2 finishing hours, and 2 carpentry hours. We would like to know whether this change keep the current basic variable optimal or not. Again, using the idea of the duality, we are going to check the feasibility of the dual solution or the CBVB inverse, whether it is still dual feasible or not. Same as before, we start by identifying the change that we do in primal. So we have a new column for table. How does it affect our dual problem? So in the dual problem, it will change the entire table constraint. So we will have a new table constraint that says 5y1 plus 2y2 plus 2y3 greater than or equal to 43. So that is our new table constraint corresponding to the new column in the primal problem. Same as before, we plug in y2 equals 10, y3 equals 10, and then we find out that the sum of the left-hand side, 40, is not greater than or equal to the right-hand side, 43. It means that the current basic variable in the optimal solution for the primal problem is not optimal anymore. The reason is because the dual solution, the old dual solution, is no longer dual feasible when we have the new constraint. From the previous slide, we conclude that the current basic variables are no longer optimal because the current dual solution is no longer dual feasible after the change. It means that the new selling price and the resource usages of the new table makes the table now becomes worth producing. Why is this the case? Again, we may check from the viewpoint of the shadow price. So we have the shadow price for each constraint. Same as before, it is still 0, 10, and 10. And then this is the amount of resource used by the new type of table. And then we multiply the shadow price with the amount of resource that is used. And then we know that to produce this new type of table, the value of the resources that we use equals $40. With the selling price of $43, it is clear why the new type of table is worth producing. Now let's talk about the last change about adding a new activity. Now suppose Dakota would like to manufacture a totally new product, which are footstools, and then it has the selling price of $15, uses 1 board feet of lumber, 1 finishing hour, 1 carpentry hour. Does the current basis remain optimal? In other words, are we going to produce footstools or not? Because in the current optimal solution, we do not produce footstools. Okay, so we are going to add one column, let's say X4, to denote this new product. And then in the dual problem, it means that we will have a new constraint for footstools. Same as before, we are going to plug in our optimal dual solution to this constraint. So 10 plus 10 greater than or equals to 15. It means that the current dual optimal solution, or the CBVB inverse, remains dual feasible. So it means that the current optimal solution for the primal is still optimal. Okay, so even after we add a new constraint, the dual solution is still dual feasible. Therefore, the current optimal basic variable for primal remains feasible. In other words, we do not want to produce footstools. Okay, so here's a question. So you have seen that to determine whether a table is profitable or not, we use shadow price. So we use shadow price, we multiply it with the amount of resources that are used to produce a table, and then we know that the total value for the resources to produce a table equals $35. And then we compare it with the selling price, $30, and then we say, oh, that's why we do not produce table, because the amount of resources equals $35, but the selling price is only $30. Now the question is, why do we use shadow price to do this, to value the resources? Okay, I will give you a pause on this video to give you the time to think about this question, and I will return with the answer. Remember that the definition of the shadow price of a resource is that how much one additional unit of that resource increase our objective function value. So in other words, we may say that the shadow price is the value of a resource, such that we may just multiply how much we use that resource times the shadow price, and then take the sum of all the resources to get the total value of resources that we use to produce a product like a table. Okay, so that's the end of this video, in which we use the concept of duality to perform sensitivity analysis. Actually, I still have one question for you to think about. In this section, we only talk about change 1, 4, and 5. Now, if you would like to think about this a little bit more, I would like to ask you why we cannot perform the sensitivity analysis for change 2 and change 3 using the duality concept, in which we check the feasibility of CBVB inverse in the dual problem. Okay, so that's the end of this video, and see you in the next one. Thank you.